All right. So thank you, Ken, for the introduction. Thank you, everybody, for joining me here tonight. So when I started making this presentation, first I started with coming up with a name, and I thought Universe of Sound. It connects everything. I thought it was pretty clever. And then as I started doing the research to put this presentation together, it turned out that let's see if I can get my clicker to work right. That NASA beat me to it. So, so NASA already has a project called A Universe of Sound. It's a collaboration with the Chandra X-ray Observatory, and they produce these things called sonifications. So data sonification is the process of taking astronomical data, like from an image or from a graph, and then turning it into more of a musical composition rather than an image. And we're going to take a look at some of those a little later in the presentation. And for anyone that wants to take a look at what NASA and Chandra have come up with, here I have a couple links, and I'll loop back to this slide at the end of the presentation in case anyone wants to take a picture of that. Go to those links yourself, check out some of these sonifications. But first, I wanted to go into the history of astronomy and how we've started sonifying data rather than using visual representations. So essentially, for all of human history, astronomy has been an inherently visual science. If you want to experience the night sky, you'd have to just look up at the sky, see it for yourself with your own eyes. And for anyone who happened to be visually impaired or blind, then the only way for them to experience the night sky would be to have someone else describe it for them. And with some of the earliest astronomers, besides just their eyes, they had plenty of tools that they would use, again, with their eyes. So including astrolabes, sextants, quadrants. Those were all used just measuring the positions of stars with just your eyes. So these astronomers really took eyeballing it to a new level. Now, so as we started depicting the night sky, it turned out that the earliest known depiction of the night sky was actually a tactile representation of the sky, meaning it's something that you could feel and not just look at. So this here is an object called the Nebra sky disk, which is the earliest known depiction of the night sky, dated to somewhere between 1800 and 1600 BC. So this was discovered in 1999 near Nebra, Germany. And it's a bronze disk about 12 inches in diameter. And each of these little dots represents stars. We believe that this represents either the sun or the full moon. Over here we have the crescent moon. This arc down here might represent a kind of boat. And then there would have been two arcs on these sides here. And from what I understand, they represented the east and west horizon. So you can kind of see the sun and the moon traveling from east to west. And then you'll notice there's this little bundle of stars right in the middle. Does anyone want to guess what that's supposed to represent? Yeah, the Pleiades. So you can see there's 7 different stars here for the Pleiades star cluster, or sometimes called the Seven Sisters. So we believe that that might have been the earliest depiction of the Pleiades star cluster. Now, as I mentioned, this is tactile, meaning you could feel it, you can touch it. So anyone who is visually impaired, if they happen to have access to this Nebra sky disk, they could feel it to feel where the stars are, to feel the shape of the full moon, to feel the shape of a crescent moon. But there's no way for us to know whether this is how the Nebra sky disk was actually used. And there are some other ancient examples of tactile representations of the sky. For example,
how large is that disk?
It's about 12 inches in diameter. So fairly small, kind of portable.
What
yes.
is this made out of?
Yes, so all this kind of bluish area would be bronze, and then this is gold inlaid into that. So you could, you can move your fingers across it, feel where all the stars are, feel the shape of the moon and the sun. Now this over here is, and I want to get the name right, this is known as the Dendera Zodiac. So this is a relief sculpture that was found in Dendera, Egypt, and it was dated back to about 50 BC. So this zodiac is a map of the night sky, and it contains, see, I have it in my notes here. It depicts 72 constellations, including the 48 constellations in Ptolemy's catalog. And so those constellations from Ptolemy, those are the ones that are, or some of the ones that are officially recognized by the International Astronomical Union. So they include some of the actual official constellations we recognize today, including, I think if you look somewhere over here, you might recognize Scorpius. And this also depicted the 5 visible planets. So this, since it's a relief sculpture, also would have been tactile, but since it was carved, this was carved into the ceiling of a chapel dedicated to the god Osiris. So we can probably safely assume this wasn't meant to be touched for any visually impaired people. Now, so thousands of years ago, there were craftsmen making these objects, which could have been used as tactile representations of the sky. Don't really know if that's what they were used for, but these days, we can pretty easily make our own tactile representations of the sky using 3D printers. And I have a few 3D printed objects here, some of which we made right here at the planetarium, including our own little constellation discs. So we have kind of like a raised relief sculpture of the constellations of Orion. Let's see, I have Canis Major here. What else? I've got the Big and the Little Dipper, so I'm going to pass these around. You can take a look at those, kind of feel where the stars are instead of having to look at where they are. We also have a 3D printed model of the phases of the moon, so you can feel the shape of the moon rather than having to look at it. And I think I'll start this one at the back. And then with radar technology and also satellites orbiting around different planets in our solar system, we were able to make 3D printed models of the terrain of planetary objects. So we have a 3D printed model of a crater on the moon. So this one we actually got from an organization known as NISE, N-I-S-E, but the rest we printed here at the planetarium. And so these tactile representations, they're an excellent way of making astronomy more accessible to people who are visually impaired or blind. Since they aren't able to really see the sky for themselves, they can feel what the sky looks like instead. And this presentation is going to focus a little bit more on making astronomy accessible through sound, but we'll get to that in just a bit. Now, after hundreds of years, so even though there have been tactile representations of the sky that have existed for thousands of years, it wasn't really, the usefulness of these kinds of representations wasn't recognized until much more recently, especially now that we have 3D printers that can create these depictions of the sky. So as time went on, astronomers, they began depicting the night sky in a much more two-dimensional way. Here we have one of the oldest complete star catalogs, known as the Dunhuang star chart, which was dated back to about the 7th century in Tang Dynasty, China. And so this is the oldest complete star atlas, which depicts 1,345 stars and 257 constellations. And this was in the 7th century. And over the next several hundred years, this is basically what became the norm of depicting the night sky, either with hand-drawn pictures or in writing. So for example, even hundreds of years later, as astronomers became more precise with their measurements of the night sky, like here we have Tycho, one of the best known observational astronomers who used a quadrant to measure the positions of stars in the sky. He still had to record his observations and measurements, either in hand-drawn pictures or in writing. So here we have one of Tycho's charts of the constellation Cassiopeia. So you can kind of see that W shape to it. And then there's also this kind of surprise guest appearance up there. Does anyone know what that object is? Yeah, so this is a supernova labeled I for Nova Stella or new star. So in 1572, Tycho witnessed this supernova and included it in his chart of the constellation Cassiopeia. So now if we use a telescope to aim at that same region of the sky, we're able to find a supernova remnant, now known as supernova 1572 or Tycho's supernova. And then several years after Tycho's passed away, Galileo became the first astronomer to ever use a telescope to observe the night sky. And of course, telescopes, they're tools designed to aid the eye, because really doing astronomy was all about using your eye and using instruments to aid your eye. And Galileo, he was able to, or his earliest telescopes had a magnification of about 3 times. So he was able to get a closer look at the planets and the moon. But again, he had to record his observations with paintings and drawings and in writing. So here we have Galileo's watercolor paintings of the moon as he saw it through his telescope, revealing craters in the moon. Thank you. And so again, these drawings, these paintings, they're really only accessible to people who can see them. You can't feel them, you can't hear them, or anything else like that. So you'd have to just look at these observations as other astronomers saw them. And then again, much later, around the 1850s, astronomers began to be able to collect their observations or take their observations more directly. So in 1850, Frederick Scott Archer developed the wet collodion process. So you take a glass plate, you cover it in a gelatin mixed with some silver salts, and then that salt reacts to visible light by turning opaque. So we basically have a negative image of astronomical objects. So these two pictures here, now these were taken in 1903 and 1923. So around that time, this is when people would still be referring to these objects as spiral nebulae because we didn't really know what they were. But we now know that these are pictures of the Andromeda Galaxy. So this one was taken in 1923, and you can see this object labeled VAR. Any guesses what that is supposed to be? All right, so there we have a variable star. So this picture was taken by Edwin Hubble in 1923 at the 100-inch telescope at the Mount Wilson Observatory. So this picture and this discovery of that variable star, this is what revealed that, well, after Hubble calculated the distance to that variable star, this is what revealed that these spiral nebulae were actually galaxies of their own. This picture is what revealed that our universe is much bigger than we originally thought. And so these pictures here, again, are still really only accessible to those that can see, even though they advanced our analysis of astronomical data. It's still really only for those that can see these pictures. And these pictures, another limitation of theirs is that they can only capture visible light. But we've known since the year 1800 that there's more light than just what's in the visible light spectrum. So William Herschel here discovered the existence of infrared light by putting a thermometer next to some light refracted through a prism. So we've known since 1800 that there's light that human eyes can't see, but it took a much longer time before we were able to start detecting that light and measuring it. So in 1937, Grote Reber was the first astronomer to construct a telescope meant to observe the sky in frequencies of light that we can't see. So this is the first ever radio telescope with a 9-meter dish. And so this focused radio waves to a radio receiver up here. Now, these radio telescopes were pretty limited because the radio receiver has to be tuned to a specific frequency. And then this telescope can only observe one point in the sky at a time, and it can only really measure the intensity of that radio signal. So that's not a whole lot of information. So if you want to get a better idea of what the sky looks like in radio light, you need to use one of these telescopes and stand back and forth across the sky, and then take a whole bunch of different measurements for each of those points in the sky, and then you end up with something like this. So this is a huge mess of numbers. Now this is real data from the sub-millimeter array in Hawaii. So a lot of observatories, they make their data available and free for the public, so you can go and download it for yourself if you'd like. And this is just a subset of that data. So this is just a little screenshot of something that would have been dozens of columns wide that way and dozens of rows long that way. And unfortunately, I couldn't find a lot of information about what each row represented, but from what I can guess, I'd say these first two rows represent coordinates on the sky. This next one, not too sure. This next one, I'm pretty sure would be the frequency that their radio receiver was tuned to. These three rows, I'm pretty sure represented which antennae they were using to make their observations. And then these would have been the actual measurements of like the intensity of the radio signal. So when you look at just a whole bunch of numbers like this isn't a great way to interpret data. This doesn't really give us anything useful to understand what we're looking at. But since astronomers, they were pretty inherently understood the sky through visuals, you can take this data and reorganize it. So for example, these two rows, these two columns, instead of having two columns of the coordinate information, you could break that up into an X and a Y axis. So you could have a column and row pair representing a coordinate. And then in each of those cells, you could have the intensity of the radio signal at that coordinate in the sky. And then based on how intense those radio waves were, you could assign a color to that measurement. So for example, for very intense radio waves, you could say, I want that cell to be red. For very weak radio waves, you could say, I want that cell to be blue. And when you do something like that and then translate it into pixels in an image, you get something that looks more like this. And does anyone guess what this object is? It looks pretty different from how we normally see it. Yeah, this is our sun. So this is our sun in radio waves. So where there's red spots, that's where the radio waves were the most intense. Where it's blue, that's where they were the least intense. So what do you think would be right underneath those red spots on the sun there? Yeah, so these would be sunspots on our sun. So these measurements come from up in the sun's atmosphere. So up in the earth, in the sun's atmosphere where it's hottest, that's where we get the strongest radio signals from. And these correspond to sunspots on the surface of the sun. Now, so this picture here, now of course astronomers, they wanted to turn their data into something visual, something that they could understand, but that wasn't their only option for how to interpret their data. So for example, it might be a little hard to see, but you might notice these like kind of curves and these loops. So it reminds me of another kind of map. At least to me, this reminds me of a topographical map, kind of like a terrain. So instead of saying, I want the strongest radio waves to be red, I could say I want that to be a very high altitude, while weak radio waves would be a very low altitude. And then using a 3D printer, it would be very easy to print this as a terrain rather than a colorful map. So if I were to 3D print this, you could kind of imagine I would have a disk with like 2 mountain ranges and a valley right in the middle. So that way, someone who is visually impaired would be able to feel where the strongest radio waves were coming from our sun. And again, that's not the only option. So for example, instead of 3D printing a terrain, we could have also translated this into sound. So now I want to get into a few examples of how astronomers and other physicists and chemists have used sound to interpret their data over time. And one of the earliest known examples for data sonification comes from this tool here. So here we have a Geiger counter used to measure radioactivity. Now, so inside this Geiger counter, there's a little tube full of some inert gas, and then at each end of that tube are some diodes. Now, if you're using one of these Geiger counters, that means you're probably near something radioactive. And as those chemicals, as those molecules, as they decay over time, they'll emit radioactive particles, which can then ionize the gas inside the tube in our Geiger counter here. And then, since there are diodes at the end of that tube, that'll pull the positively charged ions to one side and the electrons to the other side, creating an electrical current. And then that current can turn on a speaker and generate a sound. So there we have data sonification. You're turning something you can't see into something you can hear. Now, so let's say if you're using a Geiger counter, one of the reasons you would want to hear whether there's any radioactive materials nearby is because, well, if you're trying to navigate like a nuclear power plant, you probably want to see where you're going. Now, even though there is a meter on here that can show whether you're detecting any radioactivity, you probably don't want to be looking down at your meter the entire time. You most likely want to keep your eyes up, see where you're going, see what you're doing. So instead, you can hear whether there's any radioactive materials nearby. So for example, you might hear something like this. So if you hear this coming from your Geiger counter, you're probably safe. That's normal. But if you hear something like this, you're in trouble. So you might want to get yourself away from whatever's causing this snapshot. So this is one of the earliest examples of data sonification, invented in 1908. But we can also apply this concept of data sonification to things that we can observe in the sky. So for example, now this is an animation of a pulsar, a very rapidly rotating neutron star. So these objects should be about the size of New York City, but have about the mass of the sun, and they can rotate hundreds of times per second. Now, since these objects are very dense, they can also have extremely powerful magnetic fields that would channel a bunch of charged particles towards their poles, which then get beamed out in these very narrow beams of radiation. And as these pulsars rotate, those beams can sweep across the sky, and depending on whether they sweep across our line of sight, they might appear to blink on and off. So I have a video of a real pulsar for you guys. If you watch carefully up there, you'll see something that looks like it's blinking on and off. Here we have the pulsar inside the Crab Nebula. And you can see that this video has been slowed down quite a bit. So it's over the course of about 30 milliseconds. So the pulsar at the center of the Crab Nebula rotates about 30 times per second. Now, if you have something that appears to be blinking that many times per second, and for a neutron star, it could be up to as many as 700 times per second, our eyes might not be able to perceive that kind of flickering. We just might not be able to tell that it's really turning on and off, but our ears might be able to tell that. So for example, now the next sound I'm going to show you guys, oh, and I should also check, is everyone at home able to hear the sounds that I'm playing?
Yes.
All right, perfect. So now the next sound that I'm about to play comes from a pulsar called PSR B0329 plus 54. And it rotates once. What's that? So this pulsar rotates once about every 0.7 seconds, or a frequency of about 1.4 hertz. And if you turn that rotating, or if you turn that blinking signal into a sound, it would sound something like this. That kind of thumping sound is each time that radio signal passes across our line of sight. Now the next pulsar, PSR B0835 minus 45, rotates once every 0.08 seconds, so much faster rotation. That's a frequency of about 11.2 hertz. And it would sound a little bit more like this. Now you can kind of imagine that thumping sound 700 times a second is the fastest rotating pulsar. That's something that might be easier to perceive with your ears than with your eyes, because our eyes just might not be fast enough to be able to tell that something's blinking on. Yeah. So those are a couple of examples where we sonified something that doesn't really make sound, but we use sound to be able to observe it and experience it in a way that we wouldn't normally be able to. But there are other phenomena that occur in our universe that do happen, or that do occur with kind of an oscillation to them. So for example, gravitational waves, those cause oscillations throughout our universe. They are ripples in space itself. But those ripples in space, they happen at frequencies that are outside the range of human hearing. So there's another form of data sonification known as audification, basically meaning you take a frequency and you either speed it up or slow it down until it's within the range of human hearing. So here we have a picture of one of the observatories that's part of LIGO, the Laser Interferometer Gravitational Wave Observatory, for anyone that doesn't really know what an interferometer is. So in this building down here, they have a laser beam. And then it shines through something like a laser splitter that would split that one beam into two beams going at two different angles. And these two tunnels here have to be pretty much exactly the same length. And then that laser gets reflected back to this building here. Now, the cool thing about lasers is that light from a laser is coherent, meaning that the waves of that laser light, their crests and troughs, they occur at the exact same time. So if these two beams travel to the ends of these two tunnels, get reflected back to this building down here, and they're still coherent, then they do something called they constructively interfere with each other. Their waves add up with each other so that their signal becomes stronger. But if those waves were slightly out of phase with each other, then the peaks and the troughs of that wave, they wouldn't match up. They would do something called destructive interference, where they would kind of subtract each other out to the point where there might not be any light received in this building at all. Now, for gravitational waves, since they cause space itself to ripple, as a gravitational wave passes across this observatory, depending on what direction that wave is going, it could make one or both of these tunnels either slightly longer or slightly shorter, and it'll oscillate back and forth, making that tunnel longer or shorter, causing some either constructive or destructive interference. And we can measure that. So the first time that we actually measured gravitational waves was in 2015, when we detected these waves traveling through space and actually making these tunnels stretch and contract. So those frequencies are outside of the range of human hearing. But if we were to speed that up, I also wanted to show you what causes gravitational waves. So very compact objects like neutron stars or black holes, if there happen to be a binary system, they can orbit around each other and create these gravitational waves that ripple outwards through space. And as they emit these gravitational waves, these objects begin to fall into each other. And as that happens, they'll start orbiting around faster and faster. And for anyone that might be familiar with our little coin gravity well at the back of the lobby, so when you drop a coin in, it starts spinning around faster and faster the closer it gets to the center of that well. So the same thing happens with these black holes. And then, since they orbit around faster and faster, the frequency of these gravitational waves also increases. So if we could take that change in frequency of those gravitational waves and bring it into the range of our hearing, it would sound a little bit more like this. And this one takes a second. So that little whoop at the end there, that's those two black holes merging together to make one much larger black hole. Now, another kind of phenomenon in our universe where astronomical objects have some kind of oscillation to them, we can actually find inside stars, including our sun. Now, stars are not perfectly stable objects. So at the center of a star, you have nuclear fusion, basically like trillions of atomic bombs exploding all at the same time, pushing out, trying to rip that star apart. But since stars are so massive, their gravity will pull them back towards the center. And there's this constant battle of pressure pushing out and gravity pulling in. And that will make the star kind of oscillate and vibrate in all these different ways. So here we can see what are called the vibrational modes inside that star, basically all these different ripples happening all over the star. And the study of these vibrations inside a star is called astroseismology. So very similar to how we detect seismic waves from earthquakes here on Earth. We can also detect these waves traveling through a star. And then we can learn about the interior of these stars based on how these waves travel through that star. Now, since stars are constantly kind of vibrating, they're sometimes called good bells. They kind of act like a bell, they're kind of ringing. So when you sonify this kind of a vibration inside a star, our sun would sound more like this. And to me, this sounds kind of like one of those singing bowls, those crystal bowls you can rub a pot on. So this is what our sun would sound like if it were emitting sound waves and if we could hear it through space. There's a lot of sound and almost like music coming from our universe. So I've been talking about sonifying actual phenomena, but there's also more of an abstract way to sonify data. Now, this here is a CCD chip, or a charge coupled device. So inside this chip, this is broken up into a bunch of little pixels. And underneath each pixel is a capacitor, a photosensitive capacitor, meaning that when light hits those capacitors, here we go. So as a photon strikes those capacitors, then some semiconductor material will emit an electron. And then the more photons that hit one of those capacitors, the more electrons get emitted, the stronger the current you get in each of those capacitors. So you can measure the voltage across each capacitor, and it will tell you how many photons hit that one specific pixel. So you can tell your computer, I want that voltage to be translated to how bright that one pixel is going to be. And then these CCDs here, they were invented in 1967, and they can be used to detect anywhere between near infrared and X-ray, depending on what kind of coding you might put on your CCD here. And these are what are used in most digital cameras these days, including the ones inside your phone. Now, so when you take a picture using a CCD, you would get something more like this. So now we can actually record color, we can record brightness, we can get these very vibrant images of things in outer space. So again, we're going to circle back to our Pleiades star cluster here. But this, what we're looking at, is just a computer's interpretation of the data collected from a CCD. But if you could take a cross-section of this picture and then look at what the data is really telling you, you would get a curve kind of like this. So this curve would tell you how many photons were collected in each of these pixels. So above each star, you would have a higher point in the curve, more photons, a brighter pixel. And where there are less photons detected, it would be darker. So that's a pretty natural way to think about collecting photons, turning it into an image. But again, we're just interpreting data. There are multiple different ways to translate this data. And one of those ways is to, instead of saying, I want more photons to mean brighter, we could say, I want more photons to mean louder. We could say, I want different colors to mean different pitches, different instruments. So there's a lot of different ways we can interpret that. And there's also some free apps that are available to everyone to use to sonify their own data. For example, so there's this app called Two-Tone, which is a free open source app that you guys can all use. For any astrophotographers here, if you happen to have your images saved as like FITS files, you can upload your image to this app Two-Tone, and you can make a little musical composition to go along with your image. And you can select, so in this app here, you can select what instruments you want to be used for your little composition. You can just select like what scale you want the notes to be playing. So there's a bit of freedom here. It's not as advanced as some of the ones that I'm going to be showing you next, because the next ones were made by NASA and other observatories. But I'll show you guys some examples of what this might look like if you took your data and turned it into a musical composition instead of an image. So here we have a picture of the Eagle Nebula. And once I play this video, you're going to see two lines over here on the side. There's going to be one just straight vertical line, which will show you a cross-section of the data. And then there's also this kind of squiggly line here, which basically shows you the same thing, how bright each pixel is at that point in the picture. Now, in this particular sonification, so we have a combination of X-ray data from Chandra and also optical data from the Hubble Space Telescope. And any pixels down here will be heard as a lower pitch note. Pixels up here will be heard as a higher pitch note. And the brighter the pixel, the louder it will be. So let's hear what that sounds like. Pretty spooky. Yeah. And so you can tell that for this particular sonification, they chose basically one instrument. It's all the same instrument, just playing at different volumes, different pitches. Now, the other cool thing about data sonification is that we can take the visual data and break it up into its different components. So just like how you can look at this one object in X-ray and in optical, you can do that with sound too. So let's listen to what just the X-ray part of this image would sound like. So now it's a little bit easier to tell that down here these stars have lower pitch, up here a higher pitch. So for anyone who is visually impaired, who can't see these images, they could instead experience them through sound. And then I figured I'd also show you the sonification of the optical version of that image. So here we have a pretty new and interesting and even more accessible way for everyone to experience the universe and the night sky. Because now you're not limited to just what you're looking at. You can also experience what we're looking at through sound. and we can break that sound up into different wavelengths that we want to observe. So this can help us to dig a little deeper into the images that we're seeing, to break it up into layers, to learn more about what's happening inside these objects here. And as I mentioned, for this sonification, they use pretty much one instrument, but you could also choose a variety of instruments to create a more musical composition. So next, I want to show you guys. Here we have the Carina Nebula captured by the James Webb Space Telescope. And again, this one is going to go from left to right. Now this one, let's see, they chose, and very similar, down here, these pitches will be lower, up here, pitches will be higher. Now, all of this kind of gaseous, dusty area, that's going to be kind of a droning sound, whereas the stars are going to be played by piano notes. And the ones with these long diffraction spikes around them, they'll also have like a little bit of a symbol to them. So let's hear what that sounds like if you put a little more thought into turning your images into a musical composition. So once you add a little bit more of a variety to your instrumentation, you can also introduce visually impaired people to different objects that you're looking in the sky. You could be looking at a nebula, you could be looking at a star, you could be looking at a galaxy. Now you can give people more of an idea of what they're experiencing through what they're hearing. And in both of those sonifications, we had it sweeping from left to right. But depending on the symmetry of the object or the picture that you're looking at, you might want it to go in a different direction. So for example, this object here is a star called Aris Puppis and the constellation Puppis. And since it's got more of a circular symmetry to it, instead of going from left to right, they go from a ring around the outside to a ring around the center. And again, they have lower pitch at the bottom, higher pitch at the top. And the stars are going to sound like bells, and this dust around the star at the center here is going to be vocals. So let's take a look at how that sounds. And I think that one is one of my favorites that I've seen so far. So using data sonification, we can make astronomy more accessible to more people who might be visually impaired. And we can also kind of open up a new way to experience the universe around us and more ways to explore those objects and kind of go more in depth into them instead of just limiting ourselves to what we can see. So thank you guys for being a great audience, and I'll take any questions if you have any.